Alright, let me go back to the previous lab. The lab you're working on now. I just want to take a look at this business of the counter, because this is kind of like the shift register we just talked about. It's something we can do with flip-flops. We can build a counter out of flip-flops. And the counter that you're using, a 7493, actually looks like this inside. So let me go to the data sheet for that. 7493. And let's demystify this figure that we see down here. Further down, right there. So, logic diagram, it says this is what the 7493 looks like logically inside. It's a bunch of JK flip-flops. Well, that's kind of weird, right? Because this is supposed to be a counter, and it's comprised of a number of flip-flops. And these flip-flops have a clock input with a little bubble next to it, which means the clock is effectively inverted. Now, most of the flip-flops we've worked with, stuff happens when the clock rises from 0 to 1. If we invert the clock, then stuff will happen when the clock drops from a 1 to a 0. Okay, if the clock looks like this, then the inverse of the clock looks like this. And if we feed the inverse of the clock into the chip, the action happens right here and right here, which is on the falling edge of the clock. So these little bubbles that you see on the inputs is just a shorthand way of saying these flip-flops are active when the clock falls. Okay, sometimes these are called negative edge-triggered flip-flops as opposed to positive. So that's one thing. These flip-flops are active on the negative edge. That's when stuff happens. They're JK flip-flops. The J's and K's are not connected to anything. And we are supposed to take that to mean that the J's and K's are both logic 1. Now, there's not necessarily a good reason why that should be the case. But that's how this logic diagram is set up. Is the J's and K's are both logic 1. Well, what does a JK flip-flop do when J and K are both 1? Anybody remember?
Inverse, right?
Yeah, it becomes a toggle flip-flop, so Q will go to the opposite or the inverse value on each clock tick. So we can think of these as toggle flip-flops where T is 1. Every clock tick, when the clock goes from 1 to 0, the output's going to change. So let me redraw this diagram, and then I'll show you this redrawn picture. So I'm just going to label my outputs QA, QB, QC as before. But look down here, where does the clock come on this lowest flip-flop? It comes from QC. So QC is connected to the clock input of that bottom flip-flop. And where does this third flip-flop's clock come from? It comes from QB. So QB is connected to that third flip-flop's input. And where does that second flip-flop's clock input come from? Well, it comes from input B. But remember what I said, tie input B to QA. So we're making another wire from QA to this clock input. So QA feeds that bottom, that flip-flop below it, that clock input. And then input A, remember that gets connected to our clock signal from the 555. So if we go inside the 7493 using this logic diagram, here's the circuit that you're building. Let me see something. I knew it. Alright, that should be clearer. here's the circuit that we're building. So our clock goes into this first flip-flop's clock line, but the Q output goes into the second flip-flop's clock. That Q goes into the third, and so on and so forth. So what does this do as we drive the clock? Because it's just 4 toggle flip-flops, right? Where the toggle input is 1, so these are always going to toggle. And they're negative edge triggered. So let's draw a picture. Timing diagram. And let's suppose that these are starting off low. And so to indicate that, sometimes I'll draw a little dotted line over here, so that we know these are low. Okay, on the first falling edge of the clock, we know one thing that's going to happen. This flip-flop's going to toggle its value. So QA is currently low. Now it's going to go high. Is QB going to change at all when that happens? What do you think? What's going to happen to QB's clock input? Right here, the clock input for QB goes high. Does that cause any change in QB?
I want to say no.
Yeah, say no. Right? It's negative edge triggered. So if this clock input dropped from a 1 to a 0, that would do something. But simply changing from a 0 to a 1, that has no effect. So QB is not going to change. And since QB is feeding the clock input on QC, this was a 0, it's still a 0. QC is definitely not going to change, and neither is QD. So on that first clock edge, right, when the clock drops, the only thing that happens, QA goes from a 0 to a 1. But let's look at the next clock edge. So what's QA going to do right here? So yes, you're right. Positive edge. Okay, so let's go to the next negative edge. Yes, so on the positive edge, QA will not change. So here's the negative edge. Clock is dropping. Now what does QA do?
It inverts.
Right, it inverts, because that's what T flip-flops do. When the clock drops, QA is going to change to a 0. Well, now something else interesting is going to happen. Because this is the clock input on QB, and that input just changed from a 1 to a 0. Which means QB is going to invert. Since this input, this clock just changed from a 1 to a 0, QB is going to toggle. And since QB is the clock input on QC, QC's clock input just changed from a 0 to a 1. Well, that doesn't do anything, right? Action always happens for these on the falling edge. So QC is unaffected. And since that's QD's input is still just a 0. It's been a 0 from the beginning of all of this. QD is not going to do anything. But then when we come out here, there's another falling edge. So we're starting to see the pattern now. QA is going to toggle, which means QB's clock changes from a 0 to a 1. Well, that doesn't do anything. So QB stays high. So QC's clock input stays high, doesn't affect it. QD is just hanging out with a 0. But then on this falling edge, something really good happens. So falling edge on this clock, QA is going to toggle. So it goes low. Well, this is QB's clock input. Since the clock input is changing from 1 to a 0, QB is going to toggle. QB is going to go low. Well, this is QC's clock input, so QC's clock input just changed from a 1 to a 0. That's going to make QC change. And QD still just hanging out at a 0. So what do the values of QA, B, C, and D look like? Right here they were all zeros. Right here it was a 1, 0, 0, 0. Here was a 0, 1, 0, 0. Here was a 1, 1, 0, 0. Here was a 0, 0, 1, 0. It's counting, right? 0, 1, 2, 3, 4. And this pattern will repeat for 4 more cycles until eventually this input will come down to a 0. And at that point, since that's this last flip-flop's clock input, that falling edge of the clock input will cause QD to change to a 1. So this is counting. And this is one way to make a binary counter out of a bunch of toggle flip-flops or a bunch of JK flip-flops. So this is logically what's going on inside the 7493. Flip-flops are fundamental building blocks. You can build so many things with them. You can build counters, shift registers, and you can build state machines. So they're useful for all kinds of these sequential circuits, these things that behave based on their past behavior, which is what's the essence of a counter, right? Its new value is its old value plus 1. So you can actually get some JK flip-flops. You can build this in Tinkercad or in the lab, and you'll see the outputs counting in this way. The disclaimer is this is considered poor design. Okay, so really important aspect of designing systems with clocks. All of your flip-flops should be clocked together by the same single clock signal. We never really want to have a clock signal coming out of anything other than the clock signal itself. Okay? Why? Because you're more prone to race conditions and glitches and other types of errors if your clocks are coming out of logic as opposed to just coming from this one clock line. So in practice, we would not build something like this for, like, a serious system. But to make, a quick counter, this is fine. It's potentially problematic from a race condition point of view, because if we start at 0, 0, 0, 0, first clock tick we go to this. The next falling edge of the clock, we actually go to this state. This output goes from a 1 to a 0, and then that causes this bit to toggle. And then on the next clock edge, this is going to change from a 1 to a 0. And then eventually, that's going to trickle around into here through this logic and cause this second flip-flop to toggle. And then eventually, that falling edge from a 1 to a 0 will go around into this third flip-flop and cause that to toggle. So to count from 3 to 4, we actually temporarily went to 2 and then to 0 and then to 4. So if we had something very, very fast looking at the output of this counter, it would be something like this: 0, 1, 0, 2, 3, 2, 0, 4. Is that a good counter? Not really. But, for some things, that works fine enough. For driving a 7-segment display and watching it count from 0 to 1 to 2 to 3, this is perfectly fine. But, if you took a really fast picture of it, you'd probably see these intermediate states. Okay, so that's just another example of flip-flop circuitry and the things we can do with this. So let's go back to lab 6. And let's talk traffic light control. So, a famous 3-way intersection is in need of a traffic signal control system, and you have been assigned the task to design and implement the system. So, same setup as before, okay? 3 lanes in a T shape, only 1 lane and 1 signal light per lane. And green, yellow, red lights. Okay, so a total of 9 LEDs. And car on the right gets priority. And any time a light is changing from green to red, it should go through an intermediate step of being yellow for 2 to 4 seconds. So suppose your intersection is set up like this. So there's west, south, and east. And let's say there's a car right here. Thank you. Okay, so usual traffic intersection, and let's say there's a car on the south. So this is going to be red, this is going to be red, this is going to be green. Okay, so your previous traffic intersection, if a car showed up here, this goes red, this goes green. Okay, that's all truth table controllable. Here's what you want for Lab 6 Experiment 2. A car shows up here, this turns yellow, and it sits there for a few seconds, and then it turns red, and this turns green. And now this car goes away, so this car has priority. This should go yellow, and then it should go red, and then this should go green. And a car shows up here and nothing changes because this car has priority. And then if this car goes away, this should go yellow, and then go red, and this should go green. And then a car shows up here, it doesn't get priority right away, this goes to yellow, and then goes to red, and then this goes to green. So like a regular traffic light, okay? That's what you're after. So your system diagram is more complex. You have 3 car sensors, you have 9 outputs. Okay, label these, pick some kind of reasonable naming system using west, south, east. So these are your inputs, these are car sensors. 1 equals car, 0 equals no car. But then 9 outputs, so something like, you know, west green, west yellow, west red, south green, south yellow, south red, east green, east yellow, east red. Or you do green west, you know, and so on. 1 equals on, 0 equals off. Usual way to do it. Alright, so how the heck are we going to do this? So sketch the intersection, document your design, implement the intersection control, demonstrate your final implementation to the lab instructor, which you won't be able to do because we're virtual. You know, system diagram, equations for, or system diagram, truth table for what you want the lights to do, equations, wiring diagram, implementation. And then take some pictures of the implementation when you actually get this to work. Flip the switches for when a car shows up. See if you're fast enough with the screen copy to capture the yellow light and then the red light and the green light. It's a little hard, you know, with a simulator, but once you get this built, it's really satisfying to see it work. So you can spend some time testing it and so on. So here's another helpful hint. There are multiple design options. One option, parentheses, the option we really recommend, is to use the logic from the 3-way intersection from the earlier labs, and then use that to generate the yellow and red lights. And there's a timing diagram here, right? When your green goes off, you want your yellow to come on for a few seconds. Yellow goes off, red goes on. Alright, so we've been talking about state machine analysis and state machine synthesis and all this stuff. And none of that stuff really applies to the easier way to do this experiment. Okay? If you try to do this using what we've been talking about with state machines, you get a really complex circuit. And I don't recommend doing that. Okay, we're going to use a trick. And this is not doing what we've been doing in the past few homeworks, okay? This is a trick. But it's a really useful trick. So think about this and ask questions about it, and this is the optimal way to design your circuit for this experiment. Okay, so here's how we can rethink about this. You did a previous lab where you made a three-way intersection controller using just red and green lights, right? So you have this, old lab, and it's got sensors coming in, west, south, east, and it's got red and green. And I'm going to look at this one lane at a time. I'm only going to draw the circuitry for the west side right now. So there's actually a red and green for east and a red and green for south. But let's just look at one lane. Let's just look at west. Okay. And this you already have. This is an old lab. 3 car sensors coming in and 2 outputs to say turn the red light on or turn the green light on. Alright. We're going to do something slightly different. So let me rename these. Let me call this old red. And let me call this old green. And we can't just send those to LEDs because this turns on as soon as a car gets priority, and then you got a big crash in the intersection. Alright, so let's think about this. Here's my old green signal, here's my old red signal. Let me do it like this. Let's suppose that west has a green light right now. And then at some point, another car comes along and takes priority. So the green light goes off, and at that point, our old red light turns on. So let's look at our new green, our new yellow, and our new red. Okay, if our old green light was on saying, yeah, you have priority, our green light's going to be on, our yellow light's going to be off, our red light's going to be off. Okay, what happens when a car comes along, say from the east that has priority, and our old circuit says, oh, turn the green light off, turn the red light on, right? We don't want to immediately turn the green light off and the red light on, right? We want to turn the green light off, but we want to turn the yellow light on. And we want to leave the red light off for a little while. And then a little while later, we want to turn the yellow light off and turn the red light on. So we want this kind of behavior from our new circuit when we're getting this kind of behavior from the old circuit. Everyone still with me? And then let's say all the other cars go away, so now our west lane has priority. Our old signal says turn the green on, turn the red off. Well, we don't really want to turn the green on right away because somebody else had a green light and we want their light to go yellow for a little while. So we're going to wait a little while and keep our green light off, keep our green light off, keep our red light on, and then a few seconds later we'll turn on the green and we'll turn off the red and we'll keep the yellow off. So we want this kind of behavior. All right, so here's the trick. Let's take our old green signal and let's put it through our delay circuit. So let's make delayed old green. So delayed old green is going to start off high. And when it drops, we're going to have this 2 to 4 second delay before it drops in response. And when it goes high, we're going to have this 2 to 4 second delay before it goes high. Okay, and I'm not going to worry about the old red signal at all, because old red was just the complement of old green. So I'm going to remove that completely from here. But what I'm interested in is this old green signal and the delayed version of the old green signal. And if I look at these two signals together, that's enough to determine what my new signal should be. So over here, when old green is 1 and delayed old green is 1, my new green should be 1, my new yellow and new red should be 0. Okay, when I lose priority, when my old green goes to a 0, and my delayed old green is still a 1, that means I just lost priority, like very recently. And that's when I want my new green to be a 0, but I want my yellow to come on. After 2 to 4 seconds, my old green is still 0, but my delayed old green has changed to a 0. That's when I turn off my yellow light and I turn on my red light. And then when I start to regain priority, so my old green is a 1, but my delayed old green is still showing that old 0 because it's only been, half a second. I still want my green off, I still want my yellow off, and I still want my red on. And then over here, we're back to our original condition where the green was 1, the delayed green was 1. That's when we go green and no yellow and no red. So you want to think about this, okay? And you want to try to make your own version of this and convince yourself that it's doing something reasonable. And once you believe that this, describes how your circuit should act, it's pretty easy to implement this. So this is a signal from your previous lab, right, saying that green should get permission. Here's that signal sent through experiment 1 of lab 6, the delay circuit. And so let's turn this into a truth table. So here's old green. And here's delayed old green. And here's going to be our new green, yellow, and red. And I'll add some comments over here. Okay, old green is 1, delayed old green is 1. That's this state down here. This is where you've had permission for a long time. Right, long enough that that green signal that you got from your old circuit has gone through the delay circuit and appeared on the output. So you've had permission for at least 2 to 4 seconds. That's this place right here, and we want your new green light to be 1. So we want to say go, don't slow down, don't stop. All right, when you start to lose permission, your old green immediately goes to 0, but your delayed old green is a 1. So that's this state here. Old green is 0, delayed old green is 1. This is just lost permission. Zero, 1, what do we want to do? Since you just lost permission, turn on your yellow light. Okay, so make your yellow 1, turn off your green, keep your red off. Alright, a few seconds later, this old green value of a 0 will get through your delay circuit, and you'll have a 0 on your green and a 0 on your delayed green. That's 0, 0. This means you lost permission. A long time ago. Long enough that your yellow light has turned off and now your red light is on. So you want red to be on, green and yellow to be off. And then the last state is when you start to regain permission. Your green signal is a 1, but it hasn't gone through the delay circuit yet. You just got back permission, so whoever had a green light is now looking at a yellow light. You just got to wait that out. So you're still going to leave your red light on and your green and yellow lights off. So this is the state where you just got permission. Waiting for someone. Waiting for someone's yellow light. So you still have to wait with your red light on. So the whole question of introducing the yellow light just boils down to this one truth table. Take the old permission signal from your old lab, run it through your experiment 1 delay circuit. Those are 2 inputs. Write truth tables for this. Green's easy, it's just this ANDed with that. Yellow is this ANDed with that bar. And red is apparently just the opposite of this. Right, 1, 0, 1, 0. So very simple circuitry on top of the circuitry from your previous lab. Run it to your green, yellow, and red. This is for just 1 lane. Make the exact same circuit for the south, make the exact same circuit for the east. Meaning, you need a delay circuit, you need the old green signal coming from your previous lab, you need the logic for generating green, yellow, and red. So straightforward, but a lot of work, lots of pieces. Okay, questions about that? This is something where you really want to be clear on the logic you're after, right? This is the behavior I want. This is absolutely the truth table I want. I have no doubts about it at all. Well, except maybe I'm not sure about this. Okay, go back and figure that out before you start building the circuit, right? I don't understand why this goes up here. Figure that out before you start building the circuit, because once you get into the circuit, it's a big jumble of wires and chips. Okay, so don't be questioning what am I trying to do when you're trying to put together wires and chips. Try to pin that down and be absolutely confident of it first. Okay, so drawing your own version of this in whatever form makes sense to you, changing it into a truth table, and then sanity checking it, right? Step away, take a walk, come back, and just look at this and say, does this make sense? If I've got a green signal, but I didn't have a green signal 2 seconds ago, what's going on? Oh yeah, my light should still be red because I just got permission. Okay, right? Convince yourself that this is what you want, and then take it as a design problem. Write an equation for G in terms of these, Y in terms of these, R in terms of these. Sketch the circuit, put it together with the lab that generates the old green signal, and you got 3 old greens, right? And then turn that into a big wiring diagram, put on pin numbers, part numbers, power connections, all of that, and then hop into Tinkercad and start building it. Alright, when you're done, you have a big circuit with 3 switches, 1 for each of your car sensors, and 9 LEDs, red, green, yellow. It really helps if you lay these out in, you know, something like traffic intersection. So here's your breadboard, right? If you can put your LEDs like this, I guess put yellow in the middle. Right, so that's kind of laid out like an intersection that you're working with, right? And then put down 3 switches for, you know, I don't know, west, south, and east. Or maybe, you know, put a switch here, put a switch here, put a switch here. It's up to you. There's different switches you can play with in Tinkercad too. But lay it out in a way so that when it's working, it's really easy to see that it's working. Because I've had lots of people working on this lab, and we get to, you know, they're trying to demo their circuit, and their circuit actually works perfectly, but they can't tell because, you know, they're looking for this LED over here to change green, and then this LED goes to yellow, and so do this in a logical way that makes sense to you, right? And then start playing with the switches, right? Be really clear, which way do I flip a switch to make a car present or not present? And start off with no cars anywhere. And now put a car on the west and make sure this is a green light. And while the car is still on the west, put a car on the south. And this should change yellow, and then red, and this should turn on green. And then take this car away, this should turn yellow, and then red, and this should go back to green. And then put a car over here. And think about how you're going to test this. Right? How many different combinations do you have to go through to convince yourself whether or not this works? That's your test plan. Okay. You know, put a car on all 3 lanes and make sure that this one is green. Now take away the south one and make sure nothing changes. Now take away the east and make sure it turns yellow, and then red, and then west turns green. And so on. Okay, this is simultaneously the most frustrating and the most satisfying lab of the whole course. Frustrating because obviously it's really big and it's error prone, but once you get it to work, it's like a really good feeling because it's a really major circuit. It's doing a lot of stuff, and it's pulling in all of these concepts, you know, from the beginning of the course all the way through to flip-flops and state machines, and it's really rewarding when you get it working. So start it early, obviously, and come to lab hours if you're not getting any progress, right? And work methodically, and you'll get there. And it's Tinkercad, so you get to keep the circuit, right? And you can even throw that into portfolio and share it with people when they're interviewing you for jobs and stuff like that. So. All right, so that's the lab. So main things I want here, right? I want to see what you're doing. I'd rather not just open your lab and on the first page there's a big wiring diagram, right? Talk about what you're doing, right? Explain your approach to all of this in your own words, right? So that you understand it, right? If you can explain it to me in writing, it means you really understand it. If you can't explain it, then think about it some more, right? And that's kind of the acid test for, do I understand what's going on? Can I put it in words and describe it to somebody else? So describe what you're going to do. What is the strategy here, right? Why is this the truth table that I'm trying to implement? And then do the usual, you know, write the equation, simplify it, sketch the circuit, so on and so forth. So system diagram, truth tables, equations, wiring diagram. And then implement it and take some pictures to show that the implementation works and talk about that. And then conclusions, lessons learned, new experiment, cover sheet on the front, you're good to go. And that's your last lab of the course. Like I say, lab 7 is an all software experiment that does not involve, you know, drawing circuit diagrams or things like that. So, all right, any questions on all of that?
I mean, for now, no. I mean, further down the line, once I start building circuits.
Sure. Yeah, when I say no questions, if you don't answer, that doesn't mean that I assume everybody understands this perfectly. But yeah, questions up to this point. And we never really know until we actually get into it. But is that enough to get people started? Sounds like it is. All right, so let's take a quick run through the homework again. So question 1, design a 2-bit binary down counter. What's a down counter? It counts down, right? So a down counter goes 2 bits, 1 1 1 0 0 1 0 0, and then back to 1 1, and it just keeps cycling through that. It's a state machine, right? You have 4 states, and you have no input, right? Because it doesn't say anything about an input. The clock's not considered an input, but you basically have 4 states that goes back to the beginning, and you know, maybe this is state 0 0. Well, let me just call them with names. Let's just call this state A, B, C, D, and we want the output here to be, say, you know, 1 1 1 0 0 1 0 0, and then go back to 1 1. So there's a state machine for a 2-bit down counter. So design it, and you've got 3 designs to do: one with D's, one with T's, one with JK's. And in the solved problem, they build an up counter. So it's similar, but again, please don't just take this and change all the ups to downs. Okay? Forget about the solved problem. Just take this as, you know, I'm taking my exam and I've been asked to make a 2-bit down counter using D flip-flops. How do I do that? And use that to test your understanding of the process, right? And if you can't remember steps, write down steps, put those on your notes, and so on and so forth. If you get totally stuck, I can't remember what the first step is, you can look at the solution for 1S, right? All right, question 2, design a binary counter that counts from 2 to 7 and then restarts from 2. That's a 6-state machine, right? You want something that goes from, you know, state A to B to C to D to E to F, and then back to A. And it should count from 2 to 7, so to get to 7 you need 3 bits, so your output here should be 0 1 0, that's 2 3 4 5 6 7, and then back to 2. So same thing, you've got 6 states, you've got no inputs, you've got 3 outputs, and you design that machine using D's, T's, or JK's. So another design problem. All right, question 3, this is a different way to look at a finite state machine. You have 2 states, A and B, and you have 2 inputs, X and Y. And this is saying if you're in state A and your input is 0 0, your next state should be A and your output should be 0. If you're in state A and your input is 0 1, your next state should be B and your output should be 0. If you're in state B and your input is 1 1, your next state should be A and your output should be 1, and so on. So you have 2 states, you have 4 input variables, you have 1 output variable. So you're starting from this, you can make your normal state transition table, right? And then go from there to a machine. And so here they want you to do two different things. So the first one is using full encoding with T flip-flops, which means 2 states, you can use 1 T flip-flop. And if your output is 0, we could call that state A. If your flip-flop has a value of 1, we could call that state B. Okay, or the other way around. 1 hot encoding says use 2 flip-flops. So you're going to have a pair of flip-flops, T1, T0. It's going to have values Q1, Q0. And you might say, you know, if this is a 0 and this is a 1, that's state A. If this is a 1 and this is a 0, that's state B. And we assume those are the only 2 valid states. And when it says derive the minimum excitation and output equations for full encoded and show the implementation, just do the usual state machine design, right? Don't worry about what this exactly means. Excitation equations are basically what do you need the inputs of the flip-flops to be, okay? But don't think of that as something special. Just do the usual state machine synthesis that we've been doing for all of this, okay? And show the implementation. Question 4 is a different presentation of a state machine. So we have states A, B, and C, and we have a pair of inputs, Y1 and Y2, and we have an output RCO. Or do we? No, we don't. We have 3 outputs. So we just want to change from state A to B to C to A to B to C. And when we're in state B, we want Y1 to be 1, Y2 to be 1, and RCO to be 0. Oh, let me think about this. Yeah. So Y2 is high during state B only, Y1 is high during states B and C, and RCO is high only during state A. So use D flip-flops, design this, and if you happen to be in a state that's not A, B, or C, you should just move to state A. Otherwise, move from A to B, B to C, and C back to A. So 3 states, 3 outputs, no input. Alright, question 5 is the mood machine. So you have 4 states, happy, sad, so-so, and reset. You have an input X and an output Z. Design a machine that does this using JK flip-flops. So if you're in this state and your input is a 0, set your output to 1 and go to that state. If you're in this state and your input is a 1, set your output to 0 and stay in this state. Alright, so 4 states, they're not named 0, 0, 0, 1, right? But make a table. Decide reset's going to be, I don't know, 0, 0. Happy will be 1, 1. Sad will be 0, 1. So will be 1, 0. Right? Where by 1, 0, I mean maybe Q1 is 1 and Q0 is 0. But write it down, right? Make a little table. If Q1 is 1 and Q0 is 0, then that's the happy state. Right? So you can get rid of these words and you can change it into, you know, Q1, Q0 is 0, 0, 1, 1, 1, 0, 0, 1. Or 0, 0, 0, 1, 1, 0, 1, 1. Or whatever you want to use, right? You'll get different machines in the end depending on how you assign these states, but that's okay. You'll get the same behavior as far as transitions from state to state. So 1 input, 1 output, 4 states, JK flip-flops. All of these questions are basically, you know, what kind of flip-flops do you use? How many flip-flops do you use? What are the inputs? What are the outputs? What are the state transitions? All right, 6 needs a little detail because I don't want you to go crazy doing too much work on this. So question 6, you're designing a locking system with a keypad. It has keys 0 through 6, and it has a star key. And it's normally locked, and it unlocks only when you hit star 2, 3, 6. And any other sequence locks the system. Okay? So you have a number of states here, and you have a number of inputs. You have 7 input keys plus a star. So that's 8 inputs. I will let you be a little looser with the way you draw your state diagram for this. Okay? So normally, you know, we would have 8 arrows coming from a state that would say if this is a 0, if this is a 1, if this is a 2, and so on. I'll let you take some liberties, right? 0, 1, 2, 3. And show me what the output is, right? So find something that makes sense for you, okay? This is typically not the problem that I decide to grade, but play around with it, okay? Don't just skip it. And the way I interpret this is if you type in any sequence, the system gets locked. If you hit a star followed by 2, 3, 6, it unlocks. So if I hit star 2, 3, 5 followed by star 2, 3, 6, it should unlock after that star 2, 3, 6. All right, and then question 7, just another state machine, goes from this output to that, right? So looks like 8 states, 3 outputs, no input. And you use D flip-flops for this. All right, we're out of time. We're out of homework. Good match. So work on those. Come to office hours if you have questions. Keep working on the lab, and I will catch you next time.